Good, and welcome to this video on question 3 of the 2014 Scholl Calc exam. Again, two parts, part A and part B, where part B has an option, a choice in there. Part A is an integral, which isn't too nasty, but requires quite a bit of algebraic manipulation. Part B has a pretty strange problem, to be honest. Once you get your head around what the question's asking, it's actually not too bad, but I think that the second option, the critical path question, is a lot easier. Having said that, a lot of students, maybe yourself as well, haven't done critical path analysis as an internal assessment. It hasn't been assessed in scholarship for a number of years now, but back in this exam they were assessing pretty much every standard. So if you hadn't done critical path, you were stuck with quite a tricky problem. If you had done critical path, you're at an advantage. Alrighty, 3A. A narrow rod, 12 centimetres long, is made of a material of varying density. The density of the rod at the point X from one end of the rod is given by a density equation. It's actually the Greek letter rho there, but I'm just going to use P because I can't be bothered doing that every single time. B and R are positive constants, and X is between 0 and 12 because the rod's only 12 centimetres long. So if we just think about what this density equation is, for a couple of trivial values, we're told that B and R are positive, but look, suppose that B, actually doesn't really matter what B is because it's in the front there, but suppose R was equal to 1. If R is equal to 1, then our density equation becomes B times X, 12 minus X, which is a negative parabola with roots of 0 and 12. And if that's the case, if the density is maximum right in the middle of the rod and lowest at the ends of the rod, and it's symmetrical, that would say that the centre of mass needs to be in the middle of the rod. I know it said that R was positive, but another trivial example would be if R was equal to 0, because I guess R could be 0.00001, and then it would be essentially 0. Then we would get a density function of B times by x to the 0, which is 1, times 12 minus x. We get a negative linear equation, which would start at some highest point and drop off in a linear fashion all the way to 12. And if that's the case, if it's denser at the left than it is at the right, then the centre of mass is going to be somewhere to the left end of the rod. Maybe at 4. Okay, so that's just to get my head around what this density function is, because we're talking about finding the centre of gravity of the rod in terms of R, so we should know how it relates to what R is. We're given this integral, and we need to make that integral equal to 0. So we're integrating between, we don't actually have to understand how this integral is formed or where it came from. Although if you do some physics, you would know things like centre of mass calculations and torque calculations and all that sort of stuff, and an integral is just a sum of things. So we're summing up the density times by x minus c, which is the difference between x and the centre, and we want all that sum to equal 0. But in an exam you don't have time to think about that, so let's just go integral between 0 and 12, the density function which we're given, multiplied by x minus c, where c is a constant we're trying to find, and this integral must equal 0. What we're integrating here is just a polynomial. The first thing is b can be taken outside of the square root because it's a outside of the integral because it's a constant, and then because it's equal to 0, we would divide out the b. So b is not going to be in our solutions, so we can ignore b. because we're making this equal to 0. And then we're integrating x to the r multiplied by 12x. So 12x to the r plus 1. Actually, let's be careful with this. Let's expand out this quadratic. 12x plus cx. So it's 12 plus c all times x. It's minus x squared, and it's minus 12c. And then we're timesing all of that by x to the r. So we're integrating 12 plus c x to the r plus 2 minus x why did I say r plus 2? I mean r plus 1. Because if we've got an x and then we're timesing by x to the r, it's x to the r plus 1. This one's x to the r plus 2. And then the last one is minus 12c times by x to the r, so minus 12c x to the r. We've got 3 terms there because I grouped the 2 linear terms together. If you didn't do that, you'd have 4 terms and the algebra would become even more tedious. Apologies, I just dropped my chair. Okay, so to integrate this, the 12 plus c is a constant. We increase the power by 1, divide by the new power, increase the power by 1, divide by the new power, increase the power by 1, divide by the new power, and we're evaluating that between 12 and 0, and that equals 0. Okay, subbing in 0, the bottom limit, is just going to make all those terms disappear. 0 to the power of anything is 0, other than 0 to the 0, of course, but it's not relevant. So subbing in 12 will give us the answer we want. 12 plus c times 12 to the r plus 2 minus 12 to the r plus 3 over r plus 3 minus 12c to the r plus times 12 to the r plus 1, oopsies, over r plus 1 equals 0. Now, in each of these 3 terms I'm just highlighting, there is some 12s that we can get rid of. There's another one there, actually. Divide through by 12 to the r plus 2. Okay, I can do this because I'm trying to solve an equation. So yes, I'm going to make the expressions all different, but I'm going to divide the right-hand side by the same thing, so it all works out. If I divide by 12 to the r plus 2, the first term becomes a lot simpler. The second term will still have a 12 in it. And the third term will be this. And I want c in terms of r, so everything that's got a c will stay on the left-hand side. And everything that doesn't have a c will end up on the right-hand side. And then if I factor the c out of this, and I factor the 12 out of this, then I can put those fractions together. Be careful with the minus in this. And put the fractions together on the other one. I can cancel the r plus 2's on both sides. I can cancel those. I can cancel those. And I can also, you can see that there's a negative 1 on the left-hand side in the numerator, so it's negative c over r plus 1 equals negative 12 over r plus 3, so I can get rid of the minuses, make them pluses. And I told you this had some serious algebra to manipulate. 12 times r plus 1 over r plus 3 is how the centre of gravity depends on r. Let's just move this all up to here. Right, how does that actually compare with our two trivial cases that we considered? So checking with those. If r is equal to 1, that was the first one I considered, then c is equal to 12 times 2 over 4, which is equal to 6. Bingo, right in the middle. And the reason I included this little bit of explanation in this video is the first time I did this problem, way back in 2014 when the exam came out, I lost a minus in my integral, I think it was, or I might have stuffed up the power. Could have been both, actually. And I came out with an expression that looked good, but when I tested that out for various values of r, I ended up with a centre of gravity outside of the 0 to 12, outside the rod. Now, I don't think that's possible, so that made me go back and check my integration, and I found the error. And r equals 0, 1. If I make r equals 0, even though it strictly was greater than 0, I get c is equal to 12 times a third, which is equal to 4, which actually was the answer I was guessing earlier. Okay, part B. A family of functions, interesting, is built from two functions f and g with a new function h of p of x, I just think HP source when I read that, defined for each value of p between 0 and 1. These functions are shown in figure 2. Okay, so f and g, the building block functions, are actually quite simple. And then this h function, which depends on a constant p, is kind of a random function. Powers the f and powers the g by a different amount. And then we've got another function, s of p, which represents the difference between the max and min of h of p. Find the exact value of p that maximizes s of p. My goodness. So it is a differentiation problem. We're trying to maximize s of p. We need to find out what that s of p function actually is. S of p is the difference between the max and the min of h of p. So I need to find the max and min of h of p. Now, to find that, I could diff this and make it equal to 0. And I did do this. It's a bit tedious, and it proves something that the graph below actually shows us, so we don't need to. The graph has been given here, and what you should see, y equals f of x and y equals g of x are the solid lines. This one here is g of x. That's equal to 26 plus sine x. And it hovers in and around 26. Your basic understanding of trig functions should tell you that sine is a function that bounces between minus 1 and 1. So the maximum value of that is 27, and the minimum value of that is 25. And they occur at specific values of x, right? They occur at x equals pi over 2, and the minimum occurs at x equals 3 pi over 2. Okay, so if you know what the sine x graph looks like, then because both of the f and g functions, both of these functions here are just vertical shifts of sine x, when we take f and g, we know that they both line up in terms of their mins and max. And then the h function is powering them. And if we're powering a function, the biggest value of the power will occur at the biggest value of the base. So looking at the other function just before we get that, f of x is down the bottom one. That's f of x. Okay, so that has a minimum value of 1, and it has a maximum value of 3, because it's bouncing in and around 2. 2 plus 1 or 2 minus 1 is the min and max. And you can see the dashed ones represent h, and the max and mins line up. And that's what I was saying before, that if you're powering f of x and g of x, then the biggest base will generate the biggest value, and the smallest base will generate the smallest value. So let's find out what this s of p function is. It's the difference between the max and min values of h. So we've got s of p is h max minus h min. What are those values? Well, the h max is going to be when f of x and g of x are the biggest. So h max is going to be 3 to the power of 1 minus p multiplied by 27 to the power of p. And h min is going to be the smallest value of f to the power of 1 minus p, which is 1. 1 to the power of 1 minus p multiplied the smallest value of g of x. Again, because they line up, the minimums and maximums both line up. So 25 to the power of p. And I want you to notice that both of these are base 3. The h max one is 27 is 3 cubed, so we get 3 to the 1 minus p times 3 to the 3p, which is 3 to the 2p plus 1. And the bottom function, 1 to the power of 1 minus p, is just 1, so we get 25 to the p. So h max, 3 to the power of 2p plus 1. Minus h min, which is 25 to the p. And the question asks us to find the exact value of p that maximizes this s, maximizes the difference between the max and the min. And you can see from the diagram here that if we just look at a couple of cases, so for example, let's look at this one here, the max and the min, the difference is that big, whereas in this value of p, the difference is that big. And somewhere in the middle here is when the difference is the biggest. So we're looking for a p-value somewhere between 0.5 and 0.8. Okay. To find the maximum value of something, we diff and make it equal to 0. So s of p needs to be differentiated. S dash of p. We need to remember how to differentiate expressions where the base is not e. Like if this was e to the 2p plus 1, it would just diff to 2e to the 2p plus 1. But the base is not e. We use implicit differentiation if we want to derive it, but the examiner actually gives us a hint. If a is a constant, the derivative of a to the x is ln a times a to the x. So we're going to use that knowledge. Okay, so I'll just make a note of that. The derivative of a to the x is equal to ln a times a to the x. In other words, it diffs to exactly the same thing, but you times by ln a. So if it was e to the x, it would diff to ln e times e to the x. Ln e is just actually 1, so that's why we get e to the x differentiating to itself. Okay, so this first one's 3 to the 2p plus 1 is going to differentiate to ln 3 times itself, times 2 because the chain rule applies still. The power is not x, it's 2p plus 1. And then 25 to the p is ln 25 times 25 to the p. And this equals 0 at a max or a min. And we need to solve this equation for p. So 2 ln 3 multiplied by 3 2p plus 1 equals ln 25 times 25 to the p. Going to divide. And now we need to, well, we could use logs actually. But I think it's quite a sneaky little trick here. If I write this bottom term, 3 to the 2p plus 1, if I write it as 3 to the 2p times 3 to the 1, and then the 3 to the 2p can be written as 3 to the p all squared. Do I want to do that? No, I don't want to write 3 to the p all squared. I want to write 3 squared to the p. And the reason I've done that is because now there's only a p in both of the numerators. Okay, I'm going to take that bottom right 3 up to the top, so I've got 6 ln 3 over ln 25 equals 25 to the p over 9 to the p, because 3 squared is 9, and then that's 25 over 9 all to the p. Okay, that's the sneaky thing, because we can now make the equation only have a single power in it. Okay, then we log both sides, doesn't matter what log you use. Bring the p down the bottom, and then divide by log of 25 over 9. My goodness, this is a pretty tricky problem. Okay, I'm just going to evaluate that on my calculator and just check that it gives me an expression in the ballpark of what I was aiming for. Lots of brackets needed. Gives me 0.7016 to 4dp. Just checking the schedule. Yep, that's exactly right. And it was inside that region we were looking at between 0.5 and 0.8, where that arrow was the biggest. Okay, just going to move that out of the way for the next question, critical path. The critical path question, like I was saying at the start of this video, if you had knowledge of critical path, it was the easier of the two options. It gave you a diagram in the book to speed it up, because critical path's an internal assessment on its own. Usually takes around an hour to solve the problem. They've given us a network diagram to speed it up, and they bring in this twist about crashing, which we're going to learn about now. There's lots of good videos on critical path on YouTube. If you're interested, just pop it in the comments and I can link you to a couple. A toy developer is designing a new product to be manufactured in its factory. The design team has identified 11 activities and their precedence relationships. The project needs to be completed in 38 weeks. Find the critical path, crash the project to fit the 38-week deadline, state the changes that you make and their effect, and find the most economical crashing cost to the clients. Wow, lots to do in this. Note a network diagram of project duration times is in your answer booklet on page 26 and 27. So they've already summarised all of the precedence relationships, all of the durations, and they've just put it there. So critical path, you require a forward pass. So starting the project at 0 with a duration of 4 for task A will finish it at 4. This means task B and task C can start at 4. 4 plus 7 is 11. 11, 5, 16, 16, 15, 31, 4, 3, 7, 7, 6, 13. So just to summarise what this notation is, this is an early start time and this is an early finish time, meaning that at the earliest we can start task A at 0, and at the earliest with no delays we can start task A at 4. Task B and task C both depend on A, so the earliest they can start is 4. But then when we get down to task G here, task G depends on E and F, which means it needs to wait for E to start. So earliest start time for G is actually 31. It means that C and F can be delayed and not affect G. 31 plus 2 is 33, 33, 30, C is 35, 33, 36, 36, 40, 40, 43, and the deadline we were trying to meet was 38 weeks, and we've taken 43. So we need to crash it. Crashing means shorten the project. We need to shorten it by 5 weeks by employing more people or paying more money. Going back here, this is called a backwards pass. This is the latest finish time, and this here is the latest start time. And these are the same because K is a critical event, so is J. And the difference between the late start and the early start is a float, and these both have no float because they can't be delayed without affecting the project. When we take the backward pass, we find out that task H has 1 week float, where task I is critical and has no float. Okay, the latest that task H can finish is actually 36 before it affects task J. It starts at 33, it will finish at 35, it's got 1 week float, which means it can be delayed by up to 1 week. We take the smallest number going backwards of the tasks that are going out of it, so task G has to be finished by 33, task E by 31, so all of these tasks up in the top row become critical tasks. But the tasks C and F there, they had the ability to be delayed. So task F can finish as late as 31 before it impacts the project. 31, the difference between 13 and 31 is 18. So there's 18 weeks float. And so does task C. But that's a total float. That's a total float for task C and F. Total can be delayed by up to 18, not 18 individually. So it could be like task C delayed by 10, task F delayed by 8, and the project would still be on time. Okay, so the last thing is the numbers there. That there is the number in the middle. There's what we call the float. Okay, so we need to find 5 weeks somehow. So, network diagram completed. Need to shorten project by 5 weeks somehow. So then we look at this, these crash costs for new product manufacturing. The tasks that we're trying to crash need to be in the critical path. If we crash, what were the options? If we crash C or F, right? C or F, it's not going to help because the project, those things can be delayed. We can take as much time as we want, well, not as much time, but we've got 18 weeks up our sleeve for those. So the critical tasks need to be the ones that we crash because they will shorten the project if we manage to do that. Okay, so let's look at which ones we can crash by A, B, D, E, G. A, B, D, E, G. I, J, K is the current critical path. We've just got to be a little bit careful because there was task H up there which only had 1 week float. That one there might switch over, the critical path could jump into a different place. So, A, B, D, E, G, I, J, K. Which ones are the most increased cost per week saved? So we've got some costs for the activity, normal costs. If we crash them, we can reduce their time, but it costs a certain amount of money. And that's why they've given us this variable here, cost per week saved, because we want those numbers to be low. Increased cost per week saved. So if we look at that one, for example, 1200, that's the cheapest task C, G, and H can't be crashed. But task J, is that in the critical path? Yep. Task J, we can crash it by 2 weeks. We can reduce it from 4 to 2. So that's good. Reduce J from 4 to 2. How much did that cost us? $2,400 extra. Normally $3,000 up to $5,400. So it's $2,400. Where's J? Okay, so crashing J makes it go from 36 to 38 rather than 36 to 40. And then that would be 38 to 41. So we've lost 2 weeks. We need another 3. What are our other options? Remember, we're trying to do it the cheapest possible way. This one, F, is that in the critical path? No, it's no point doing it. These 2,000 ones, I and K. I and K are both in the critical path. So reduce I. How many weeks are we needing to do this? I can be reduced by 1, K can be reduced by 1, I by 1, K by 1. What does that cost us? I costs us $2,000 to do that, and K costs us $2,000 as well. So it's another $2,000 and another $2,000. And we still need 1 week. We've got the 2,500 one's the next best. D is in the critical path as well. Yep, 2,500. We can reduce that by 2, but let's just reduce it by 1. And that's going to cost us 2,500. Reduce B by 1, 2,500. So the total cost of the project, $8,900. To shorten it by the required 5 weeks. And let's just chuck those numbers in. So J was going to go from 4 to 2. So cross there to make it 2. I is going to be reduced by 1. So it's currently 3, it will be 2. K is by 1. So it's now 2. And B by 1, so it's now 6. Let's do the forward pass and backward pass real quickly again. 0, 4, 4, 4, 6, 10, 10, 5, 15, 15, 15, 30, 4, 3, 7, 7, 6, 13, 30, 32, 34, 34, 34, 36, 36, 38. Bingo. Then going backwards, 38. Notice that both of these, the earliest they can finish is 34. So they're both critical now. We've actually got 2 critical paths. But then C and F can still be delayed. What are C and F, just out of interest? Receiving materials and purchasing materials. So we can purchase them later and we can receive them later as a result, but probably in a COVID setup. This is 2014 though, but purchasing materials, do it as early as possible, because the thing that you're going to get delayed on is the receiving of them, couriers and whatnot. Oops, that can take up to 30, so 17 float now. But the top row is critical. So, in summary, there are 2 critical paths. There's the critical path that goes A, B, D, E, G, H, J, K, but there's also the second path that incorporates task I. there are now two critical paths. A, B, D, E, G, H, J, K. A, B, D, E, G, I, J, K. So I wasn't a critical activity earlier, or was it? Sorry, H wasn't a critical activity before, but now it is as well.